NanoHub U, online instruction.
Hey everyone, this is lecture 110. So we're continuing from the previous topic of the 1D periodic waveguides to what are essentially 2D photonic crystal slabs. And so here's what they look like usually. They can either be basically an array of rods in air, or more commonly an array of air holes in a high dielectric medium, like maybe a semiconductor slab or wafer. Okay, and so again, the key concept is very similar to before, that we'll use a combination of index guiding in the non-periodic directions and then photonic crystal confinement in the periodic directions. And so here's an example of the kind of band structure we get. If you go back to the last lecture, you can understand how we end up having like a light cone in the blue region that kind of looks like this. The only difference from before, of course, is that we're exploring a different Brillouin zone, right? So then if you look at the Brillouin zone, we're going from gamma to X to M. And so that's actually what gives rise to this curvature as you go in this direction from X to M, because the absolute value of K vector is increasing kind of like quadratically, or more precisely, you can calculate it through the Pythagorean theorem, but it's not a straight line. But you can see that for the gamma to X line and then the M to gamma line, those are both straight lines that are adjusting the magnitude of the total K at the same rate that you're adjusting like the K parallel, okay. And then a similar dynamic is happening in the second picture, which is showing basically a triangular lattice of air holes in a high dielectric medium. And so, of course, it depends on what kind of structure you have as to whether you have a TE, TM, or both as a band gap. But you can see that in the left-hand side, clearly this kind of structure with air rods in air has a tendency to give you TM-like gaps for many of these radii, whereas this kind of structure more easily will give rise to both TE and TM-like gaps, but we actually need to increase the air hole radius from what's shown here in order to get both TE and TM at the same time. And so in terms of what happens when you introduce defects into the system, then you can see that if you basically shrink a whole line of these rods that are in air, like this, basically, then these will become like a line of defects that can guide light in exactly the region you want and the frequency that's otherwise in the band gap, right? So it's kind of giving us a controlled way to guide light down this thing. And so what's really interesting is, if you remember before, we said in 2D photonic crystals that we could guide light in this manner. But now we're saying that actually you can do this in a slab. And a slab is actually something that's much more experimentally feasible than an actual 2D photonic crystal, which theoretically has infinite height, right? And you can see here clearly that this, although it looks very similar to the 2D photonic crystal simulations from before, you can see that when we look at it kind of from the edge, like down the x-axis, then actually it does have a very finite height, right? So it's not super tall at all, but it's just tall enough to help confine light in the y direction. And of course that increases the cutoff frequency a bit, but if you make it taller, it can be a relatively modest effect. And so that kind of smoothly transitions us to the quote-unquote true 2D photonic crystals. And so this overall structure has relatively low loss. And then as you adjust the speed of the propagation through this structure through various means, like basically adjusting these dots here, basically the cylinders, and both the epsilon and then the spacing between them, then you get different groove velocities. And then the losses will go, of course, inversely with the groove velocity. And if groove velocity is extremely slow, then we actually have this extra term that losses go as 1 over the groove velocity squared. So that does actually limit us from going to groove velocity of 0 for just an arbitrary structure. And still having low loss, of course. So makes it a little harder to just stop light in its tracks, but you can certainly slow it down a great deal compared to free space. And here, again, it's a very similar concept as before, except we just have a point-like defect instead of a line of defects. And you can see that, again, light will be attenuated in both the x and y directions as we step away from this defect that's in the middle, which is shown in red. And then again, from the side view, you can see that it's also confined in the z direction, which is good. And then what's really interesting about these point-like defects is actually the quality factor is very dependent both on the shift in the effective epsilon associated with that point-like defect. And you can actually see there are two types of point-like defects, one in which you just have a single point, and one in which you actually have an array of points which create like a little cross, with 3 rods in both directions, right? So a total of 5 rods. And the quality factor for this larger structure is actually bigger. And the reason is basically because like when you have less mode confinement, you can have higher quality factor. So that's like kind of a general rule because it actually looks more like a index guided mode. So in the next lecture, we'll kind of wrap this up and then move on to 3D photonic crystal band structures.